Chemical kinetics. Kinetics refers to the study of rates of chemical reactions and the mechanisms by which they occur. The rate is the change in concentration per unit time. So the rate is simply how fast a reaction occurs, and the mechanism is the pathway or series of steps by which the reaction occurs. There are a couple theories that we're going to look at with kinetics. The first one is collision theory. The fundamental idea of collision theory says that in order for a reaction to happen, the atoms, molecules, or ions must first collide. If I increase the concentrations of the reactants, that results in a greater number of collisions. In order for a collision to be effective at converting reactants to products, two things must happen. Number one, there must be a certain minimum energy present in order to rearrange outer electrons in breaking bonds and forming new ones, and they have to have the proper orientations toward each other at the time of collision. So I've given you two examples here. This is an ineffective collision. I will tell you why. The idea is that they have to have enough kinetic energy and they have to collide at the proper orientation. So let's assume that carbon monoxide is coming in from this angle, water is coming in from this angle, and I want to form CO2 and water. Well, if they collide at these angles, there's no way to get CO2 here in the intermediate step. So what happens is, since I don't get CO2, the molecules bounce off one another and nothing happens. Now, in a collection of molecules, you will have ineffective collisions because there are millions and millions of molecules, and they're not all going to collide at the proper orientation. So you will have ineffective collisions. In order to have an effective collision, if they have the proper kinetic energy, they also collide at the proper angles. So in this example, same reaction. I want to form CO2 and water, and you'll notice that CO is coming in from this direction, water is coming in from this direction, and when they collide, you see that we can actually get CO2 as a product because the carbon hits the oxygen at the right angle. And so I get the product CO2, and then the hydrogen break off, combine, and give me H2. So they had enough kinetic energy and they collided at the proper orientations or proper angles. Second theory is transition state theory. We're going to look at this one-step exothermic reaction, so it's going to release energy. Transition state theory says the reactants pass through a short-lived high energy intermediate, which is called a transition state, before the products are formed. So my reactants were A2 and B2. The transition state right here in the middle is an intermediate, and it's simply where we're breaking old bonds and forming new bonds. And so you'll see their dashed lines here because we're breaking old bonds and forming new bonds. And then we have my products on the right. So as you go through a reaction, you go through this transition state. The activation energy, E sub A, is the energy that must be absorbed by the reactants in the ground states to allow them to reach the transition state. So let's look at a graph of potential energy versus time for an exothermic reaction. I'm going to label a few terms here. We're going to start off with reactants, which are right here. A2 plus B2. My products are over here. At the top of the curve is the transition state, which is that intermediate. It's always the high energy intermediate. It's at the peak of the curve. E sub A is the activation energy. You have to have enough energy for the reaction to occur. So this activation energy is the energy barrier that we must overcome in order for the reaction to happen. And then delta E is the distance between reactants and products. Now this is an exothermic reaction because the products are lower than the reactants. So we are releasing energy in the course of this reaction. If we flip this reaction over, we get an endothermic reaction. Same reaction, but I've flipped it over, and so my reactants this time are AB, and my products are A2 plus B2. Notice that energy barrier is a lot greater because I have to go from AB up to the transition state, so that E sub A is a lot larger. Now delta E doesn't change. Delta E is the change in energy for the reaction. It's endothermic though, so it's requiring energy for this reaction to happen. There are some factors that affect reaction rates, that is how fast a reaction occurs. One of those factors is the nature of reactants. H2 plus F2 reacts very fast, but H2 plus O2 reacts slowly. Now these are hard to predict as far as the nature of reactants. The second thing that affects reaction rates is the concentrations of the reactants, and we're going to spend some time on concentrations because this is one of the things that we can predict and look at a reaction and determine how the concentration will affect the reaction rate. So let's consider the reaction of 2 moles of iodine chloride and 1 mole of hydrogen in a closed container. So here's my balanced chemical reaction. 2ICl plus H2 forms I2 plus 2HCl. I can express the rate of reaction in terms of any one of those reactants and any one of those products. If I want to express the rate of reaction is change in concentration per change in time. Well, delta means change. So if I want to express it in terms of ICl, it's change in concentration of ICl over 2 delta T because there's a coefficient of 2. Now, the reason there's a negative sign here is because ICl is a reactant and reactants get used up. I can express the rate in terms of H2 if I know the data for H2. There's a negative there as well because it's a reactant. So it's simply the change in the concentration of H2 per change in time. I can also express it in terms of products, and there's no negative sign for the products because products are formed. So that's how we express the rate of reaction, change in concentration per change in time. So for this reaction, here is some actual data with the rate, and I will show you how we get those rates. I'll use the data for ICl between 1 and 2 seconds. So let's look at that data between 1 and 2 seconds for ICl. So the rate is equal to negative change in concentration of ICl over 2 delta T using the information from the previous slide. So the change in concentration for ICl, I'm looking between 1 second and 0 seconds. So the change in concentration is negative 1.348 minus 2.00 over 2 delta T. Well, the change in time is just 1 second. If you actually solve that, negative 1.348 minus 2 divided by 2, you will get a rate of 0.326. And rate is expressed in molarity per second. Molarity per second. You'll notice what happens with the rates. If you look at this column right here with the rates start off really quickly, 0.326, and then it goes down 0.148, 0.09, 0.062, and that's always what happens in a chemical reaction. The rate starts off relatively quickly, and it slows down as the reactants get used up. So here's a graph of concentration versus time for that same reaction. And what I want you to key in on here, a couple things. First of all, the concentration of ICl and H2 decrease. Those are reactants, so their concentrations decrease. Concentration of HCl and I2 increase because they're products. But notice what happens if I compare HCl to I2. HCl forms at a quicker rate, and that's because there are 2 moles of HCl formed for every 1 mole of I2. So the reason HCl forms quicker because 2 moles compared to just 1 mole for I2 in the balanced chemical equation. If I want to get the rate of a reaction at any time t, if I want to get the rate at this time right here, I could simply take the slope of the tangent line of any one of these curves. But I could take the slope of the tangent line, and that would give me the rate at any particular time t. So the rate of reaction at any time t is the negative of the slope of the tangent to the curve at any time t.